Okay, so here we go. We'll complete lecture module 5 today, chapter 5. We've already covered some of this. I wanted to start with this screen just to, again, realize where we're at. So we know the operating system is the resource manager. We know that the operating system operates in protected mode, also known as super user, root mode, kernel mode, because again, the operating system is the only thing that can access the resources. And we know there are physical and logical resources. We discussed that. The operating system and its managers provide the necessary abstraction. Again, think about the file system, right? We don't interact with the physical device, seeing where our files are actually fragmented across the system. We see them as the logical file construct. So yesterday we did cover the device manager, the memory manager, and the file manager. And today we'll pick up with the scheduler, which is responsible for CPU management, cover security and network management, and then also some other categorizations, classifications of operating systems and their functionality. So I'll scroll down and pick up where we left off. Almost there. Okay, so here we go, the scheduler and scheduling. To begin, we have to understand a few concepts. The notion of preemptive versus non-preemptive scheduling. Preemptive scheduling is based on interrupts. And to understand interrupts, I'm going to present the difference or distinction between interrupts and polling. And I'll use an example just in our everyday lives. Consider your phone. Consider your phone with text messages, and consider if you could not have the phone vibrate or make an audio alarm when a text message came in. What would we have to do? I'd take my phone out of my pocket. Did I get a message? Nope, put it away. Take it out a minute later. Did I get a message? Nope, put it away. Take it out. Did I get a message? No. This is polling, okay? And as you can see, it's not very efficient because equivalently, I'm using essentially CPU cycles. I'm using my resources, distracting me from whatever else I was doing to check or poll the status of the device. Modern operating systems use interrupt-driven because we know with our phones, I can have it vibrate when a text message comes in. So I don't even have to think about it. When I feel the vibration, then I pull it out. So I haven't wasted any other time continually checking it. This is the basis of preemptive scheduling. So what we have is a process can be stopped or preempted from its execution. This occurs naturally with CPU time slice scheduling. What we have is a multitasking environment. So when I'm saying multitasking, I'll just constrain the discussion to a computer with a single CPU. So of course, only one process can be executing at any one time. So the scheduler will, in round-robin fashion, assign the CPU to a process. It'll get a very small time slice, say 5 milliseconds. And of course, 5 milliseconds is fast for, it's a lot of time for a CPU moving at 3 gigahertz. But for us humans, we don't even really notice that this switching is taking place. And I just introduced another thing there, switching. We're going to see that when a process is preempted, interrupted, and another one begins, a context has to switch. Think about what we saw with the fetch execute cycle simulation, right? A computer, a process was running. It had values in its registers. We know from architecture that it's also going to have information in the cache and also the RAM. That was the cache coherency problem. So when a process is interrupted and stopped and another one is resumed or begun, we need to save the system state. So a system state for a particular process is where it was in the execution. Recall we had that instruction pointer, and recall we had that fetch execute cycle, and the textbook described it as fetch, decode, execute, store. But I also added something in there because we have the program counter. It's actually fetch instruction, increment program counter, decode the instruction, execute the instruction, store the results. So the first thing we did there was increment, right, add 1 to the program counter, the instruction pointer, excuse me. Recall what I said, this was expectational. So should this process be interrupted and stopped, it was pointing to the next instruction to be executed, expectational. So it can pick up where it left off. And again, the operating system has to save the system state because again, it has values in registers, it has all the whatever's in the cache, maybe that needs to be flushed back out to RAM. And as the operating system saves this system state, well, it's saved in memory, in a little portion of memory. So you're actually consuming memory to save the system state of a process that's been suspended. And then, of course, the process that's going to be resumed, its system state is put back into place. So wherever, what were all the register values it had when it was last suspended, things in the cache, etc. Okay, so processes can be suspended or interrupted for many reasons. One, their time slice could be over. Other events could be that interrupts occurred due to input and output. Okay, right now my system is just sitting here. I just have, you know, the browsers open. Whereas I could open a different browser, open a different program, which of course is an event, would generate an interrupt, and the operating system, of course, would now show me the display for that new process. It would resume that process. I/O is one of these, input-output, is one of the reasons that can generate these interrupts. Maybe the system was waiting for input-output to either occur or to complete, okay, print jobs, things of this nature, and won't go back into spooling, etc. Okay, so we understand that. So multitasking. When we talk about multitasking, again, right now, I'm just talking about a single CPU. We recognize our CPUs are now multi-core, okay? But if I have a single CPU, I can still run many different processes in or from memory. And again, what is happening is the scheduler is in turn, in round-robin fashion, assigning the CPU to the different processes. When a process is suspended, of course, we save the system state. When a process is resumed, we restore the system state, the values of the registers, things of this nature. This switching is known as a context switch. And again, this is occurring so quickly, you know, the time slices are 5 milliseconds. The user isn't even aware of it. It looks like everything is occurring as if we had many different CPUs, because the CPUs, again, we've seen, are so quick, 3 gigahertz, 3 billions of cycles per second. Okay, there are other things that we can do to enhance efficiency. One is multi-threading, okay? We consider a thread is known, often deemed or termed, a lightweight process. The distinction between a process and a thread, or multi-threading, is multi-threading shares an address space. Again, recall from the demonstration, the fetch execute cycle simulation. I showed memory. When a program is executed, it becomes a process. It, of course, gets memory allocated to it, but it has 3 distinct segments in memory. Recall it had that code segment where the instructions were. Then it had a data segment, variables, things of this nature, and then a stack segment. With multi-threading, they share that data segment. So it's very easy for one thread to write information to it, whereas another thread can retrieve the information. And what we avoid is inter-process communication. Inter-process communication, say between processes, incurs a much higher overhead. They don't share an address space. You actually may have that same data replicated in memory, okay? Because you just transferred it. Well, now it's in 2 places. So obviously that's not as efficient from a memory management perspective. So multi-threading does provide advantages in terms of efficiency. Okay, multiprocessing and parallel processing. Both of these imply that we have a CPU with multiple cores. This was presented back in architecture, and I just, again, brought the slides forward and back. It's probably easiest to describe based on the graphics, the pictures. So if we look at this, what we have in this first sequential processing is we have multitasking. We have a single CPU. And what do we have? We have 4 processes running. We have a word processor, a browser, an email client, and a spreadsheet all running. And what we see is that time slices, the CPU, is going to be allocated to each process in turn. And note, they're not the same length. Why? Because we have an interrupt-driven architecture. Okay, so multiprocessing and parallel processing both require multiple cores. So in this picture, we're seeing essentially systems with 2 CPUs or 2 cores. The difference between multiprocessing and parallel processing is in multiprocessing, which is much less complex, processes will get assigned to a particular CPU and they will not migrate. So in this depiction, we see on the first CPU or the first core, the word processor is running and the spreadsheet is running, okay? And within this first single core, first core of the 2-core CPU, we do see that multitasking still takes place. So this is still applied, but of course it's just applied at this level to that one CPU. The second CPU will be handling, okay, the processing for the browser and the email client. Now, parallel processing. Parallel processing will actually take the application and split it up. This is very complex, by the way, to actually analyze an application and see where there aren't interdependencies. Okay, this portion of the program can run and it's not going to affect other portions, okay, or other portions are not dependent upon it. Okay, typically we'll only see parallel processing in really your high-end computing centers, you know, Knowles Atomic Power Lab, Weather Systems, Palo Alto. We're talking about supercomputers quite often. So that is the distinction, again, between multiprocessing and parallel processing. But note, again, within each, we still do have multitasking taking place. Okay, security. Well, again, the operating system is responsible for, it's the resource manager, so it's responsible for security. And we understand the 2 modes of operation. We understand user mode and we understand protected mode. Okay, where protected mode, the operating system has privileges to do essentially anything. Looking at security from the standpoint of identification and authentication. And again, I'm going to go into this in much greater detail when we get to our chapter on security. Real quickly, identification is when a user establishes or provides their identity. Authentication takes place on the computer side, right, or server side, where the computer will, of course, collect the identification information. It will look and say its password file, do we have such a user? And the password they just provided, does that match the password in my password file? If so, then yes, you're authenticated and the system will provide that user with authenticated authorization to resources. There are 3 different levels of this identification authentication scheme. You can think of it as something I know, something I have, something I am. Those are the 3 different levels. The least secure, easiest to hack, is just something I know, username and password, right? This can be password cracked, it can be spoofed, quite a few things can occur here. A little more secure would be something I have. So say I have a USB dongle and I have to insert it into the computer so the computer can verify, yes, that's actually a valid USB drive. If this is used, if these latter 2 methods are used, typically it will be 2-factor. So not only will I have to insert that USB dongle or RFID card, whatever, but I'll also have to provide a username and password. The most secure, of course, is biometric, something I am, fingerprint, retina scan, facial recognition. Okay. But again, we're going to look at this in much greater detail when we get to the chapter on security. I also want to introduce that within modern operating systems, we do have built-in firewalls now. They have SPI for stateful packet inspection. And I can't really talk about this until we cover networking. But I did want to recognize that modern operating systems do contain firewalls. And I do recommend that you turn it on, okay, in your security settings. It may not be on by default. So, and over time, you should probably keep checking it because they can get turned off. So do that as well. I have an asterisk here for updates, okay? We've seen with our mobile apps, with our mobile iOS, mobile operating systems, our desktop operating systems, that there are almost always updates over time. A lot of these updates, they may fix functionality, but a lot of them also will shore up the vulnerabilities that were later identified. The onus is typically on the user. Now, the user can say, install these updates automatically. So that's one thing the user can do. It's up to you if you do that. If not, I do recommend that you continually check for updates and update your system. And again, as I mentioned yesterday, also your device drivers, okay? The device drivers can be a vulnerability, and recall where they are in that system stack, architecture, device driver, operating system. They too can be operating in protective mode and therefore access your logical and physical resources. Okay, looking at security utilities. And again, sometimes, some of these utilities, we consider them part of the operating system, part of the kernel, and whether they actually are or not. But we have many other utilities, add-ons, so to speak, antivirus, anti-spyware. And we'll talk about these in much greater detail when we get to our chapter on security as well. So, networking. Networking is included in all modern operating systems. And what that really means is they actually have and manage the TCP/IP protocol stack. This is short for Transmission Control Protocol and Internet Protocol. And again, this is going to take considerable time when we present networking. So I'll defer my presentation on the TCP/IP stack until our chapter on networking. Manages wired and wireless connections. Okay, we know that as well. We should always be using encrypted connections whenever possible. The remainder of the chapter really is just a classification, categorization type presentation, and I'll present some of it. Some of it is just straightforward, and I will not represent that as it's just straightforward in the textbook. So yes, we can distinguish between operating systems on their intended use, whether they're a personal desktop system or a server network operating system. We know about mobile operating systems, Apple iPhones versus Android, okay? Embedded operating systems. Now, just something to remember with embedded operating systems. Of course, there's a computer, increasingly embedded in many of our devices. And of course, as soon as we put a computer in a device, it inherits all the properties, all the vulnerabilities of computers, which means, of course, they can be hacked. We're going to look at this again in security. Cars can be hacked, all of these things. And here's a question for you. I just mentioned that the onus is on the user to update their system software, largely because vulnerabilities are identified over time. How often are we updating our embedded operating systems? Recall what I said yesterday too about device drivers. Quite often, time to market is very important. Being the first manufacturer to get a new product to market can have an incredible competitive advantage. As such, they may rush the code of their device driver, or even if it's an operating system that was developed just for that device, that operating system. So keep that in mind. Okay. The textbook presents this as, how network operating systems work. Well, little misleading here. What is actually being depicted here is more of a thin client architecture, much like we have in our academic computing environment, our ACE. Okay, if you look at the computers on campus, they appear to be running local versions of the operating system, and they are, but that desktop operating system is also encapsulated in a client shell that is in continual communication with the server. More and more we're seeing a desktop case here rather than a server. So network operating systems know that they are an encapsulation, okay? They put the desktop operating system into essentially a container. And of course, our ACE environment, I won't go into this now, I'll get to it when we get to systems analysis. They can be refreshed, ghosted in mass from the server. And I'll speak about that when we get to systems analysis and design. Types of processors. Of course, our processing, Moore's law, continually advances. Our processors continually support new types of technology. One of which that we're going to look at in detail is virtualization. This is coming in Linux Lab 9, where everyone will implement a virtual machine. I'll talk about this in just a minute. We know that mobility and wearables, there's a big rise in that. And again, as soon as we do that, and we'll talk about this when we get to security, there are a lot of privacy concerns with wearables because, of course, they're tracking us continually, monitoring us continually. And who is actually in control of that data? There have been cases where people have had monitors on them, heart monitors, things like that, but yet the companies that have or maintain the heart monitors, the manufacturers, wouldn't actually share that information back with the patient. And that's questionable in my opinion. When we look at mobile computing, we have to look at the constraints. I've introduced these in the past. When I look at my phone, what are its constraints? Well, it has limited functionality or visibility in terms of input and output, but we saw how we could overcome this. A Pico projector could take a phone and project it onto the wall. We saw the Cellulon Cube that allows you to create a virtual keyboard on any surface. Great. Okay. Processing power, our phones actually have considerable processing power. Should we need more, of course, if we have a network connection, we can take advantage of cloud computing resources, servers. Okay. So that can be overcome. What is still a major limiting factor, of course, is power consumption. And associated with mobile computing, of course, power and batteries. So I want to introduce virtualization. We're going to, again, look at this in much greater detail. So our contemporary architectures and our operating systems are now enhanced and well support virtualization. So first, what is virtualization? If you ignore these three items here, if we just look at the architecture, the host OS, and an application, we saw this before. This was that stack, okay, the system stack. We know the operating system is this intermediary software, performs abstraction, or another way, transformation. I introduced that term, because nobody here up at the user level really wants to deal with the architecture, right? The ones and zeros, or even if it's represented in hex, right? Abstraction provides this nice, easy to use interface to, of course, the application layer or the end users. So this is what we're accustomed to. Virtualization software is installed on a machine at the same level as an application. It is an application, okay? So when we install VMware in Linux Lab 9 or VirtualBox or Parallels, there are many different variants, it's getting installed at the same level, the same way as we would install Microsoft Word, okay? So it's actually operating in user mode, okay? It does not have access to the resources, which are accessed again by request to the operating system, and the operating system performs these actions in protected mode, super user mode, kernel mode, root mode, okay? When we install virtual machine software, what that software does is it actually replicates the machine architecture up at this level, which allows us to install additional operating systems, guest operating systems. This is the host operating system. And in this guest operating system, I can, of course, install applications. So we can actually think of this as a virtual computer, the virtual machine. The advantages of this, of course, is that I can install many different operating systems. Why is this important? Consider software development. I'm writing programs. I want to be sure that I can run these programs on every platform. Of course, in my room here, I could, buy machines. I could have a Windows XP machine, a Windows 7 machine, a Windows 10 machine, Linux machines, okay? And then I have a room populated with machines. And then I take a thumb drive and I walk from machine to machine and test the application, okay? Clearly, this is not real efficient. My room would be very hot too. But with virtualization, just as an example, on my Mac here, I'm running VMware. I'm running Windows 7, Windows 10, Windows XP. I'm running a few different distributions of Linux. So I have that in a single machine. We have cybersecurity students in the class. Think about investigations. When a digital forensic scientist goes to investigate a machine, they don't investigate on that machine. If they do anything on that machine, they would corrupt that chain of custody. They have to leave the machine as is. So what they'll do is they'll take an image of the hard drive and put it on a different machine and work on that machine. Now, of course, that machine must be native. So if you're investigating a Windows 7, you need a Windows 7 machine. But again, I can do this in my virtual machine. There's also additional security or stability provided by virtual machines. Think about this. I have my virtual machine, my guest operating system, whatever it is, and say I have a browser here, okay? In this browser, I can browse all over the place. To some extent, I'm not even worried about getting a virus or some type of malware. Why? If that occurs, I just blow away that virtual machine. It does not have access to my host operating system and, of course, the system's resources. That's incredibly important. Think about working on programs where the programs are crashing, okay? I don't want to crash my host OS, right? My main machine, but if I crash a virtual machine, I'm saving the system state. I can restore it like that. So virtualization is a big step forward. It's being used extensively in the data centers. Why? I could, in the past, I would have to purchase a server for my web. I'd have a web server. I'd purchase one for my email. I'd have an email server. Purchase one for my application server. I will never use these servers efficiently. There'll always be cycles when the CPU is just sitting there doing nothing. It makes much more sense to buy a single server, virtualize it, and have 3 separate virtual machines for the web server, the application server, the email server, because now I can actually utilize that CPU very well. And I've only purchased 1 server rather than 3. Very important. Continuing on, of course, we know now command line interfaces do exist with our Linux labs. Desktop computing is really dominated by graphical computing, but again, there's a cost to it, right? Remember the technology acceptance model, okay? Remember OS design issues. There's always a trade-off between efficiency and convenience, okay? But we recognize, yes, command line interfaces are still out there. The book shows us the DOS, the disk operating system command line interface that is still part of Windows. And I should get a chance to show that real quickly at the end of this class. So I'll demonstrate this rather than going through this slide. So now when we look at the various operating systems, okay, what do we have? We have Windows, Apple or Mac, Linux, and Unix. And we have desktop. We really don't have desktop Unix systems. We have desktop of the other 3. All 3 do exist as servers. Okay, there are specialized Microsoft Windows servers. There's a specialized Mac server. But again, certain systems will have server capabilities, just as we introduced with Mac and Linux, secure shell functionalities built in. Okay. So I'm not going to say much about Windows. Read through it. It's important to know the history. I'll just say it that. Some of the really stable ones, Windows NT was actually very stable. Windows 2000 wasn't bad. Windows XP was good. Windows 7, I actually still prefer Windows 7 over Windows 10. And I'll take a look at some of the functionality of this too. Windows 10, of course, is the latest. Goes for that consistent look and feel. And you know, there's something interesting when we look at Mac versus Windows. Question?
Yeah, well, it's more of a comment. Windows 11 just got released yesterday.
I know. Yeah. Yes. Yeah. Thank you. Because as I move forward, sometimes I forget to mention that. So thank you. Yes. And that has some interesting aspects to it. I'll defer. I haven't really assessed it fully. I haven't implemented it, so I'm not going to just comment on what other people have written about it. So, but thank you very much. One of the things, though, I was just about to say, when we upgrade operating systems, you know, it's real interesting when you look at people upgrading Windows, you know, and there's quite a bit of commotion to it. Whereas in the Mac world, and we have some students with Macs out there, when Mac updates to a new operating system, it's almost a non-event because everything kind of stays the same. Now Windows is trying to copy this, and now moving forward, maintain a consistent look and feel. It's kind of interesting that Mac has been doing this for quite some time. Linux, by the way, you know, as I look at the different distributions or versions of Ubuntu, I notice considerable changes sometimes in the desktop of the various Ubuntu versions. Mac, of course, is OS X, is what it's referred to. Mac was developed from, it's a Unix type operating system. So it's coming direct from servers, which explains some of its functionality. I'm not going to say much more about it. One of the things, again, I introduced this back in architecture, is Apple came out with their M1 chip. And even just right out of the gate, the M1 chip proved to be superior in many aspects over the Intel-based chips. And this was without really Mac having a lot of time to optimize the operating system to use the M1 chip. So it's going to be really interesting to see how this evolves over time as well. So Unix has been around since the 1960s. This was kind of one of the first main operating systems, along with IBM, you know, the VAX. Multi-user multitasking, more expensive. Just so you know, yes, if you were implementing this in a corporation, okay, yes, it was going to cost you, it was going to be expensive to do that. But note that the Unix developers, they gave these away to universities, colleges for free. So it was not more expensive. And again, this allowed the colleges and universities to really get in and understand, explore the Unix operating system because it wasn't as proprietary. Linux is based off Unix. Okay, so we're seeing that. It was designed to mimic Unix, but to be implementable on a desktop PC on the Intel architectures. You know, Linux is now pervasive also in the data center. And there's some real interesting history here when we look at, say, the Linux Apache web server. So of course, we know that Linux is open source. So of course, its components are going to be open source. So the Apache web server is open source. And this was in the late 90s. And IBM had probably the best web server at that point. But IBM chose not to continue developing their web server because, of course, they were staffing the development team. But they realized that they were having difficulty keeping up with all of the enhancements that were taking place in the Apache web server, which was just being supported by thousands of open source developers. So here you have a clear business decision. IBM, you know, we could continue to pay these 100 PhDs or whatever to continue work on our web server, but will it ever be as good as this open source development, which is being managed by thousands of computer scientists? And they realized, no, open source was going to overtake them and actually be the better choice. So now, if you look today, if you go out and I haven't looked at the statistics recently, as of a year or two ago, the Linux Apache web server was running 75% of the world's websites. So there's its clear value there. Now we're going to see when we implement our virtual machines, we will implement Ubuntu Linux within our virtual machines. We are going to get a desktop. Okay, so we will not be confined to a command line interface. And people generally like the Ubuntu desktop and actually the operating system in its entirety. Chrome OS is a cloud-based operating system, the first. It's of course ubiquitous on the Chromebooks. And there are advantages, disadvantages to this. We've discussed some of them with cloud. When it comes to desktop computing, it depends on how much you can do offline, because again, a cloud-based operating system, those connectivity, is required. So if you have no network connection to that cloud, how much can you actually do on your computer? Okay, so what is supported in, say, offline mode? So mobile devices, well, what do we have? Of course, we have Apple iPhones, we have Androids, which are Linux-based. We have Blackberries. There are Linux mobile. There was Windows Mobile for a time, and there may still be. I just haven't kept up with what Windows is doing in the mobile environment. There are business decisions that are often overlooked when discussing the various platforms, and I'll introduce. I have a minute here. Say you are a technical officer within an organization, and you need to provide your sales force with phones, mobile phones. Well, of course, it's going to be less expensive to supply them with Androids than, say, iPhones. But iPhones provide a different level of security, largely because of the App Store. Apple manages its App Store in discrete detail. It really analyzes what is available on the App Store. It's very difficult for an app to get in there which has, surveillance, spyware, malware type properties. That's not actually true in the Android store. Many cases of what Android apps have been allowed to do. Think about this. You're providing your sales force with phones. They are going to download things, applications that they find funny or whatever. And then they'll come back to your organization and connect to your network inside your firewall. Okay. So of course, with Android, God forbid, they have something nasty on their phone that can infect your systems. And the cost of that can far outweigh what you've just paid for in terms of phones. So IT Business Society, there are a lot of considerations that we need to assess when we talk about our enterprise architecture. So Android is Linux-based. I'll let you know, of course, I have Apple. It just integrates well. There are aspects of Android I much prefer. Me being a Linux guy, I prefer Android. So I'll just say that. iOS, I'm not going to say anything about here. Blackberry. Blackberry is probably the most secure of the mobile operating systems. Android, or excuse me, Linux-based, there are versions out there, and I won't get into them. Note that there are other operating systems, the VAX, IBM ZOS. We won't get into them at this point. If you get hired by a company, I don't know if the company will expect you to know out of the gate some of these larger server operating systems. I doubt it. They're going to train you in-house. That's the end of the chapter. So now I'm going to jump to something. So give me a quick second as I change what I'm sharing here. Okay, here's my Windows 7. And I just want to alert you to this. At the bottom of the page of lecture module 5, I actually have a much more full-blown presentation on this. So if I go to my start menu, okay, the first thing I want to show you is the command line interface, DOS, within Windows. So I'm just going to type CMD. Okay, and here it is. And I realize it's very small. I really can't resize that font size or anything. So here's command line interface to Windows, my disk operating system. The commands are a little bit different. Some are the same. CD will change directories, things like that. But instead of LS, it's dir, okay? And you can see that. So, and I won't go into that in much more detail, but I can do quite a bit from the command line. In my day, we do a lot of batch processing, set up scripts, and we will get into scripting in Linux to control our system. The other thing the textbook mentions is operating systems may or may not have startup programs, startup applications. In Windows, this is managed. You can get to it a few ways, actually. I get it through my MS config manager. So here we are. Here's a lot of system configuration, but general things. Okay, how it boots, services, startup. I'm going to go to startup. Okay, and I just did this last class, so I actually removed some things. And over time, these applications, as I shake my head, will somehow re-enable themselves to automatically start. I don't find this real ethical. So what I just removed was my Adobe Acrobat, my iTunes. I just said iCloud for Windows. I don't want these starting up, taking up memory. I never use them, okay? So, and again, I am running in a virtual machine here, just so you know, Windows 7. So what opens to begin, my Microsoft Security Essentials, my VMware tools. Truthfully, do I really want Microsoft Office opening by default? No. So I'll try to uncheck that if the system will let me. It is Windows, it's going to try to prevent me. It's just a joke. And I applied that. So now I have a minimal startup when I start my computer. So essentially it's optimized. Last thing I want to show you is how to clean up your disk and defragment your hard drive. Again, Apple, Mac, OS X does this automatically, has built-in defragmentation. And we understand why that's necessary to improve efficiency. So I'll go to my computer, double click it, see if I can get it to open. Come on, it's not allowing me to open. There we go. So disk C, okay. What I'm going to do is right click or control click, and I will choose properties. Boy, it's really resisting me today. Properties. There we go. So we see tools, hardware, sharing, security, things of this nature. I do recommend you go through this, investigate it. It's going to improve your understanding of operating systems. If I were to choose disk cleanup, it'll go through and find if it has any old temporary files, cached browser files, anything I deleted that may be sitting in my trash or recycle bin for Windows that has not really been purged from the system, so I could clean up some things. In my tools, you're going to see I can check the drive for errors. Over time, your drive, some sectors, okay, will go bad, even on SSDs. It's important that we mark them and never try to use them again. Even more importantly, is to defragment your hard drive. We understand the mechanical nature of our storage devices, the mechanical hard drive. So if that read-write arm is moving a lot, it's slow. It makes sense to defragment the hard drive, and what the operating system does, it will move pieces of the file around so that they're contiguous and in adjacent tracks. So we'll minimize the necessity for that movement of the read-write arm. And then of course, if all the information is on the track, I introduce locality of reference in programming, then it can just keep reading it and read it right into that disk buffer, which is in RAM. Okay, so you can improve performance that way. Again, the full presentation of this is down in lecture module 5 towards the bottom in that video. So that's all I have for today. So lecture module 5, again, is due this week by Sunday. Other than that, have a great weekend. And